So my name's Phillip Hansel. I'm CEO, co-founder at AI Ops. We're a company that got formed all the way back sort of late 2019, early 2020, all around the whole idea and concept of, number one, is machine learning and AI going to have a place in heavy and commercial industry in a real meaningful and impactful way? And if it is, what are we going to do about it? How are we going to integrate it into the systems? How are we going to deploy these things to really make them a reliable and a sustainable engineering method for the kind of customers that we go to work for? So that is really where we got built out. And one of the things I want to say about that is key to Mobile, my business partner, Curtis Wright, is sitting over there. And he had the luxury of hearing a quote from the CEO of Dropbox, who basically said, anytime in the world, anytime that you want to do something new in the world, there's a place out there somewhere where all the people are collected and they're the best at it, right? So he was out obviously on the West Coast for Dropbox. Interestingly enough, AI Ops got started here, right here in the Southeast, because whenever it comes to process automation and control, we're the best at it. And there's a really good reason for that. Number one, we were economically accessible. We were the cheapest engineers on the market. I spent 16 years doing process automation all across this country. And I've ran into Hargrove folks, I've ran into ACE people, Prism people, all these different states, because we were cheaper, accessible, and better, in my opinion, than folks out of Denver, Sacramento, Seattle, those more expensive places to do business. So it makes sense to me what you're going to hear today about AI Ops as to what it is that we do. So to give you a little bit of concept about our team and who we are and how we go to market, we have 4 co-founders. Our team now is moving up to 9 people, but the 4 co-founders are all University of South Alabama graduates. We all have many years of process controls or mechanical engineering, chemical engineering experience in the heavy and commercial industry. We are supported by our exclusive representative, another local company, Trinova. So they are our exclusive rep here in the US, North America, Canada, and Mexico. So they also support us on the delivery of the project. So anytime that we go to work for those folks, they want to use our products, use our methods. We have a full engineering team and staff built up around that, even down to how do we train your personnel and certify them to use our software? And then how do we train your personnel to also build and do the models the way we do them, right? Which are very successful. So the first thing I want to do is sort of kind of piggyback on what Dr. Aviv was saying earlier. Is I want to put into 2 different buckets for you the things that we found to be successful in heavy and commercial industry, right? So on the right-hand side, you've got a bucket that we're going to call machine learning. And in that bucket, there are 2 modeling techniques. There's time series forecasting and classification. What are those? Time series forecasting you interface with every day when you're writing emails or any of that other stuff that is predicting the next word in the sentence as it comes down the line. Time series forecasting for us is very useful because we can predict things like upsets, those sorts of scenarios that we can lay out there. But more interestingly, what I can do is create a soft analyzer, right? Or a soft instrument, meaning where I don't have instrumentation today, I can use existing inputs, multivariable inputs, and detect what that should be. I'll give you a scenario of where we've actually done this in the real world. One of our very first customers, Sunoco LP, had an issue where they were going to have to spend hundreds of thousands of dollars to install an analyzer to understand what their real-time quality was on their reactor system. So they wanted to know the parts per million of sulfur. What we were able to do is take their lab readings that were literally on an Excel sheet. It took us about 4 months to condition the guys to actually write down the proper timestamp, but they eventually did that for us. And what we were able to do is correlate that to a certain number of inputs that did exist as instrumentation into the system and give them a real second-by-second prediction, plus or minus 2 parts per million, as to where their sulfur content was on their reactor. So the operator in his face right now has got a real-time feedback of what their actual quality is on the process there. Classification is that next modeling technique. When we think about classification, think about the old labeling setup of cat, dog, and you label it enough, pretty soon the algorithm can say that's a dog, that's a cat. We use classification in our world, in our space, to do things like anomaly detection. That's our term. Normally what you would see is on equipment failures, things like that were talked about earlier. So where you're sort of labeling out when these things happen, and pretty soon we can get a pretty good, reliably prediction that says, hey, reasonably soon this equipment's going to fail. How we actually use this in the real world, I'll give you another scenario where we've done this for another customer. These guys actually were a mining and minerals company. They took a material off a boat and they crunched it down into a smaller, finer, classified form to be used in construction material, right? Super easy. But the problem is anytime that material came off the boat, made its way into a hopper, this hopper could hold 50 tons of material, and they would want to drag it all the way down to 0 tons, right? On its transit from 50 to 0, as it's being pumped into the mill to be crushed down, this bin would plug, usually 2 to 3 times during that transit. So what that means is that they have to stop the process, they have to break it loose, hopefully with the shaker and vibration unit that they have out there, and if they can't, they have to go get and put personnel in the way, in the process to break this loose. So you're risking a person by doing that, right? Not ideal. But that was what was going on. So what they did is they came to us, they said, hey, we like your software. We know that it can integrate directly with Allen Bradley. What we want you to do is to see if we can't predict when these bins are going to plug and then give that indication to the operator. We were like, great, we will see if we can do that. And pretty quickly, within a week, we were like, hey, we can do it. And in fact, we can predict it 20 minutes earlier. So 20 minutes ahead of time, I can tell you that your bin is on its way to being plugged. And separately from that, what we want to do is then take that prediction, 0 meaning, which in this case, the number we were given over was a 0, meaning that you're not plugged at all, the process is great. 1 is there's a 100% probability that you're either plugged or you're on your way to a plug. And so we would pass that number into their control system to then start the shaker and vibration unit 20 minutes earlier, therefore avoiding the thing that we were detecting, right? So active predictive maintenance is the way we think about it. Now that's machine learning, right? And that is in general the kind of the low-hanging fruit, the easy squeeze of what's out there. That's great, we like that, we love that, but that's not what got me out of bed, that's not what started AI Ops. What started AI Ops is deep reinforcement learning. And what you're gonna see here in just a minute is a video about what deep reinforcement learning is. It is a segment of machine learning, but there is a vast ocean between machine learning and deep reinforcement learning. Deep reinforcement learning is that closed loop mechanism that we get to use, that AlphaGo scenario that Dr. Aviv talked about. It is that closed loop mechanism that we get to implement directly on a system to optimize that system. So this does the closed loop control, whereas machine learning does not over here in this bucket, right? So that is the two differences between the two. We have successful stories on 3 different modeling techniques, DQN, DDPG, and PPO. You don't need to know about those, but if you want to know the details, that's why Curtis is here. You can hit him up later. He is the expert. But what I want to do right now is sort of cement into your mind what deep reinforcement learning is. So another thing that Dr. Aviv talked about was DeepMind. They were the ones who produced AlphaGo. They also produced this video right here, where they use deep reinforcement learning to learn how to play the game Atari Breakout. I'm old enough to know what that game is, so I assume most of you are as well. But what's going to happen is this model, this AI model, this deep reinforcement learning model, is going to ingest every pixel on the screen. And from a controls perspective, it's going to use the pixels associated with the paddle moving left to right to win the game in the most optimal way possible. So from a controls engineer's perspective, that paddle is my valve, my steam turbine, my pumps, those things. After 2 hours of training, what you're going to see is that this guy never misses, right? That's great. And the way that I look at it from a process controls engineer is that's good, but you're not really winning the game. This is a standard PID loop. One of the things Heath talked about is the PID loop's fallback is it can only do that one thing well because it's concerned about the error of right now. 2 hours additional, so 4 hours total of training. What you're going to see is that this deep reinforcement learning algorithm learned to beat the game in the quickest way possible. It learned to drill through one corner of the game and then use the boundary of the game to win, right? So that is playing the game of optimization with the objective in mind, right? So how do I do this in the games that we play? Oil and gas, agrochemical, fragrance and flavor, diamond mining, gold mining, nickel mining. How do I apply that to there? That is what AI Ops set out to solve in 2019. And in 2020, we were one of 3 customers, or one of 3 companies. One of them was Emibit, which was up on the screen. The other one was Yokogawa. Their model ran for 30 days. Emibit's still around causing trouble for us, but we tend to beat them when we get put up against them. But we were able to do the closed loop control in an oil and gas facility all the way back in 2020. And we target the use of that AI directly at the factory floor. That is, in our opinion, where it needs to be. One of the things that really separates us as a company is the way in which we treat our customers and their data. Everything that we do for you gets delivered back to you, right? We're not trying to hoard that information or that technology to ourselves. And in fact, the software that we give to you lives on-prem and can be completely disconnected from the internet. I really don't even care about the data once the thing's running, right? So we don't need to see it. It can stay air-gapped. That makes IT folks very happy. I got the thumbs up. So this is a sample of the product line just to kind of give you a perspective of how wide this actually goes, and we'll talk through a couple of use case scenarios. The Kio software, which is what we built in 2020. So we solved many problems in 2019, 2020. One of which was, is it possible? Yes, okay. How do we make it reliable? Okay, we figured that out. Now how do we deploy it and execute it? That is where the Kio software comes in. It is hardware agnostic, so it doesn't matter what hardware you install it on. It is air-gapped, or can be air-gapped from the system. It is a network device with very standard protocols on it, so we can talk to 99.9% of all control systems out there. And it can handle a lot of data, and it could run hundreds, if not thousands of models concurrently, all at different scan rates. Super powerful software, really nice interface. Built by control systems engineers for control systems engineers. The Kios Cloud is that one that's really interesting. We're actually gonna go Wednesday and complete one job for a grocery store company. But you can imagine if you've got segregated assets across a country, globe, or region, and you don't have personnel there, oil and gas upstream is another good opportunity here. But grocery stores was one, chemical dosing skids is another, where you do have internet connection to these devices. How is it that from a zero trust based scenario, I can manage those devices as if I was standing right in front of them? The Kios Cloud gives you that opportunity. All the way down to the end of the line from the AI services, we can fit into any one of those bubbles or provide to you the full end-to-end service directly. The big thing that we know is to make this sustainable is that we have to teach you what it is that we do, right? You have to be able to reproduce what it is that we do. If you can't reproduce it, it's of no use, right? It can do amazing things, but 5 years from now, if you can't get a hold of me, it's not that you need to throw that in the trash can. You should be able to sustain that yourself. And we spend a lot of time with our customers making sure that they understand how to do their own development, right? We would love to be paid by you guys in perpetuity, but that's not the goal. We are a software and product company first. That is what we do. Our first scenario, this was the one, we took this screenshot in 2022, and I'll tell you why in a minute. But this was the first application we went for. This was Sunoco LP here in Birmingham, Alabama. They had a hydrotreater system. What they were looking to do was optimize their use of hydrogen. So they buy hydrogen as their raw product. So anytime that they could save money on the product that they're buying and still get the same on-spec quality product at the back end, that's excellent, right? So this is a 20-year problem that these guys had where they could not really get the balance between their control system, between performance and stability. What they were really wanting was to be super stable when things were good, but be able to perform when things were bad. And so that you can see that they kind of have this nice balance between the two. On the left is their normal control scheme and outlook and the way that that looks. And then what happened when they engaged our AI model is what happened on the right. So the way we actually do control is we don't make suggestive set points, although we can. You can technically send our predictions anywhere they need to go. In this case, we were driving the valve on a second-by-second case from our deep reinforcement learning model running on the Kio software. This model is still deployed today. We have not had to retrain it, and Sunoco is still using version 1 software, which we plan to change this year, which they have just renewed with us. So we will go up there and update them here in the next month or two when they're done with their turnaround. But what you can see is that they get a 15% reduction in their hydrogen usage. That's crazy, right? DuPont was the plant designer. They called us on the phone because they had sent APC engineers in. they had major problems trying to figure this problem out. And so because we've solved this problem, the reason why that plant shut down and being reworked right now is they're actually debottlenecking because they were able to find some other issues as a part now that they can hold this stable, right? So that plant is actually growing in its capacity as a result of this. Why this is a snapshot is taken in 2022 is because the only phone call we ever got from Sunoco as far as support on the model came on this day, and it was right after they re-instrumented the plant. And Bobby calls me on the phone and he goes, hey man, this thing's running 5% higher than what it was before. Can you tell me why? Does the model need to be retrained? And I was like, no. Why would it need to be retrained? And he goes, well, because we re-instrumented the whole facility. And I was like, oh, well, I said, let me take a look at some data because there's got to be something wrong. And sure enough, what we were able to identify is that the level calibration on one of the key inputs that we were looking at was way off. And so I called JJ, the technician, had him go verify what our assumptions were. And sure enough, that was the exact case, is that the level calibration was way off. And the AI was probably holding it still in the physical location, but we were able to still optimize and keep things going. So they went and fixed the calibration, and now they're back on track. Here's a look at the heat transfer across the reactors on that one. So you can, I don't even need to draw the line there. But the real win here was that they gave us a 2-year return on their investment. We gave it back to them in 6 months. 15% reduction in hydrogen means that they get to make claim for 346 tons of carbon saved each year, year on year, because it takes 26 pounds of carbon to make 1 pound of hydrogen at scale in our current processes, right? So not only do they get their efficiency, but now they're like a green company, right? How often does the oil and gas get to say that? This is another local customer where we were able to optimize another one of their major problems on their scenario. This is a multi-phase project here. But basically, we're able to hold these guys in their maximum performance region almost 100% of the time, regardless of feed rate changes and pushback from the back end. This is what actually resulted of that. So when we think about the use of our equipment, what we actually showed them is a reduction of that valve, for example, the work that the valve had to do. We reduced that work by 72%, but gave them a 44% increase in their actual performance, right? So you're doing your work better 44% of the time, and you're doing 72% or less of the work. Everybody would want that job, right? This is one more interesting one, and then I'll kind of break here because I got many, many slides, and I want to get to questions. But this is one that's a grocery store. So when you think about your ice cream, your meat, your lettuce, that's the refrigeration control. And this validation set right here is a set that we showed a large store chain about 6 months ago, how we can optimize their refrigeration. So of their energy costs, 40% of that is down to their refrigeration. And what we were able to show them, the purple line is what their valve does today. The green line is where that temperature goes. Anytime the green line's below the blue line, they're wasting money. Now what we're able to show them is what the red line is where your valve goes. Better use of your equipment, way more stable. And the orange line is where their temperature goes. So now you're holding and you're not wasting, right? The only thing they told us, and we jokingly said, we won't melt the ice cream. And those guys got really serious. And they were like, of all things, don't mess up the ice cream. And I was like, really? And they're like, yeah, you can't put that back in the bucket. And I was like, that makes sense. Let's start with the lettuce. So this is interesting because what we get all the time, when we talk about weak AI, which is very narrow in use case, if I have to reproduce the engineering for every single refrigerator at every single store in a store fleet, Sam's Club, for example, has got roughly 600 stores. They've got about 100 of these in each store. If I had to pay an engineer to make 100 of those models times 600, not feasible. Not for a grocery store that's got 2 or 3% margin. What we're able to figure out here is that we can templatize these models such that we can rubber stamp these out with very little engineering. Where does this go in the future? I can tell you all kinds of things about that. But I do want to get to questions. Any questions? Concerns, comments?
Phillip, I heard something at one point. If you put AI ops in every pipeline in America, what kind of reduction in emissions would you see, across the board?
We haven't ever really done that estimation, but it would be very good. And so I was actually having this conversation with somebody this morning coming into this event. And basically, you know, the big thing that we've got to understand, there's many problems here, right? One is we have an aging workforce. And I sat down and had a conversation at breakfast with the global director of Air Liquide 2 weeks ago, or last week in Houston. And he said, look, I can go hire these guys, but nobody's got my experience the way that I had it. Right? This guy literally worked with Bell Electric, the guy who wrote the instrumentation books. I mean, he of all people understands regulation and control better than anybody, right? That guy's not going to exist when he retires, and he's not going to get replaced, right? So the efficiency in my mind is, yes, you get to make best use of your current infrastructure, what we're spending a lot of our current wealth, capabilities, and everything else on, but the other sustainability piece and the other efficiency gain is in your workforce. Somebody else once said it, and I think it was the BAS gentleman, said that you can take a one person and kind of leapfrog a 20-year experienced person. What we're going to need to be able to do in our world, and the guys coming out of college today are equipped with the data science capabilities, is to be able to take these guys and leapfrog them over a 20 or 30-year process engineer that's about to retire, right? Because they're going to need to get their 2 or 3 years experience, and then they're going to need to be able to do things like this, because they're not going to have the time, they're not going to have the resources, and they're not going to have the background knowledge that it takes to do it. So I think the effect goes much further down the line than carbon emissions and the squeeze over everything else. It's our entire workforce. Yep. Good question.
So some of the examples you use are kind of are very much continuous processes. You know, looks like it was a reformer, very well known. How well do you handle things like significant delay times?
Perfect. And I'll tell you what we're doing for BASF.
Okay.
So at Geismar, we're doing one of their polymerization. I think it's a spandex is what the end product is. Yeah, PHTF. So in that case, what we want to do is reduce the time it takes to get on spec between product changes. Could take 2 to 3 days, right? Okay. Yep. So we're already on it. So Keith Deshiri,
Yep.
and then those guys are who we're working with there. So coming to you next.
All right, cool.
Yep. Any other questions?
The great part is that it's like the video game. You can look at an unlimited number of variables, both an unlimited number of tags and an unlimited number of history. So again, at Geismar, we're able to look at like the past 3 days of data before we make each control. So we can capture those time delays.
Okay.
Yeah, it's perfect. Yeah.
Yep.
All right. Thank you, guys.